that webcast and pulling it to YouTube. So give Grant a hand. All right, let me start the real talk. I'm sure I got this working. As you came in, if you saw these on the table, we have our lithographs. Tonight's lithograph is of 30 Doradus, a turbulent star-forming region, which really should be called the Tarantula Nebula, because 30 Doradus is just basically the star cluster at the heart of it. It was so bright it was thought to be a star, but it's now known to be a star cluster, and actually it's a part of a big nebula called the Tarantula Nebula. If you'd like to learn more about it, it's on the back, and it talks about star formation. But you don't have to read. You can listen to Will tonight because he's going to tell you everything you wanted to know about star formation, because our talk tonight is star formation in Orion, one of my favorite places in the universe. Next month, we will have the Milky Way's bulge from a hypothesized blob to a remarkably detailed picture. I actually wanted to call this the blob that ate the Milky Way, but David didn't seem to like that title. In August, ashes to ashes, dust to dust. The fate of stars like the sun, death of stars in August. And in September, more death and destruction, 100 ways to die in the universe. I really don't know what that talk is about. But if you would like to find out more about, remind yourself of these talks, we have our web page. Go to your favorite search engine and type Hubble Public Talks. You'll find this page. We have our list of the upcoming lectures. We have the links to the live webcasting, both on our STSCI webcasting site as well as on YouTube. We have the archives all the way back to 2005 from STSCI, so you can get your fill of astronomy should you wake up at 3 in the morning and go, I really need some astronomy right now. You can also sign up for our email list here. Let's see, the announcements, if you sign up to the website, we'll just send you, really only send you like 1 or 2 emails a month, reminding you of the upcoming lectures and telling you where you can find the webcast when it is posted. If you have comments or questions, you can send them to us at publiclecture@stsci.edu. Social media, should you want to follow us on these various things, we have Facebook, we have Twitter, we have YouTube, we have Instagram, and we have 2 or 3 on each of those channels for your social media pleasure. Myself, I'm on Facebook, Google+, and Twitter, but I'm not very active, so don't expect daily tweets from me. Observatory, I got the email from Irini and she said it's just cloudy all evening, so we will not have the observatory open after the lecture. But as I remind you every month, they do have open houses on Friday evenings. You go to md.spacegrant.org, you find their observatory page, and this observatory status box over here on the right will tell you whether or not they're going to be open. Basically, you check it Friday at around 5 or 6, and they'll tell you whether they're going to be open. Sort of like the email I get every time we have the lecture. Okay, and now our news from the universe for June 2018. Our first story, a galaxy tug of war. Well, let's start with our galaxy, okay? So this is an all-sky view of our Milky Way galaxy, and you can see right across the center here is the plane of our Milky Way galaxy. It's a disc-shaped galaxy, and we're inside that disc, so we see it as this long, straight structure heading all the way across the sky. But there are other galaxies in this image. All right, you may not know them as galaxies, but you have this spot down here, this spot down here. They are nearby galaxies. This one is called the Large Magellanic Cloud. All right. They're called Magellanic because they were discovered by Magellan on his trip around the world. Actually, they can't say that Magellan discovered them because he was the first he brought back the news of these objects to Europe. Of course, anybody can see them. They just look up if you're in the southern hemisphere. Unfortunately, we can't see them here from Baltimore. But if you do get down in the southern hemisphere, you must look up, find a dark spot, and it's just beautiful to see these clouds up there in the sky. So that's the Large Magellanic Cloud. And if there's a Large Magellanic Cloud, there's also a Small Magellanic Cloud. Yes, this is the Small Magellanic Cloud. Now, these two clouds are not clouds. They look kind of cloudy when viewed with the human eye, but as you can see from these images, they're composed of millions of stars. They are actually satellite galaxies of the Milky Way. The LMC and the SMC are two satellite galaxies that are actually orbiting around the Milky Way. How do we know that they are orbiting? Well, we can measure their dynamics and everything, but it's actually kind of easy when you look at them in radio light. Because in radio light, you see this. Sorry, I changed the Milky Way from a longitude-latitude projection to what this is an ATOF all-sky projection. But here are the Large and Small Magellanic Clouds, and you see this radio light coming along here. Okay, and you see all this junk up here, also associated with Magellanic Clouds, okay? So let me put on some graphics. We've got the LMC and the SMC, and then this is called the Magellanic Stream, okay? And this is understood to be material that has been pulled out of the Large and Small Magellanic Clouds. Due to this sort of tug of war as they're orbiting around, gravity pulls on these galaxies. And if you've got the Milky Way, which is a large galaxy, and you've got the LMC and the SMC, which are small galaxies, and they're in a tug of war, who's going to win? Yeah, you can see here the Milky Way galaxy is going to win. And you get this big tidal tail of material that we previously used Hubble observations to understand that this material actually contains material from both the SMC and the LMC. Now that's sort of what we call the trailing arm of a tidal interaction, stuff that's pulled out, okay? But stuff also pulls out on the near side due to these gravitational interactions, these tidal interactions. And this is the leading arm of it, and that stuff is actually falling into and interacting with the Milky Way. And we do not know where that leading arm material comes from. And if you just look at it sort of geometrically, right? It's closer to the LMC, and you say, oh, maybe that stuff is from the LMC. Dynamically, you can't tell. However, you can tell if you use spectra. All right, so what we did is we found 3 quasars. These are very distant, very bright objects, and their light is actually shining through this material. And so we can look in the spectrum of the quasars to see what type of material is in this leading arm. So here are the spectra. All right, quasar A, quasar B, and quasar C. And these are just, graphic artist versions of them to show the hydrogen and the oxygen concentration in these various spectra. So what we're looking at is what is the relative abundance of hydrogen and oxygen in this material. And does it match the hydrogen-oxygen abundance in the LMC or the SMC, or is it a little bit of both? The answer is it's from the SMC. So the conclusion is that the LMC is pulling more material out of the SMC that is then falling in to form this leading arm. At least these 3 lines of sight, actually I think there were 7 lines of sight through the leading arm, and the oxygen to hydrogen ratio matches that of the SMC and not that of the LMC, indicating that when you go with a Large Magellanic Cloud versus the Small Magellanic Cloud in a tug of war, who's going to win? The Large Magellanic Cloud seems to win, and that material can be traced back to the SMC. And this is the first time we've been able to get the full understanding of this full Magellanic Stream of these dwarf galaxies. And they're losing, just a small bit of their material as they orbit around the Milky Way. Yes, question?
What's the period of the orbit of these clouds around the Milky Way?
I don't know. It has to be hundreds of millions of years. Could be as much as 500 million years. Do you know, Will? Yeah, he would guess the same amount. So about a few 100 million years, maybe 500 million years, because our sun orbiting within the Milky Way is 250 million years of that time frame. So these are orbiting way outside. So I got to give it probably about 500 million. Okay.
An outer plane orbit that you're making?
Yes, they're not in the plane. They are. If the plane is here, they're down here, and they're coming. And we're not exactly sure of their exact orbit. You can sort of trace, get a feel for it from the dynamics of that, but it's still there's a still significant uncertainty in the exact orbits of them. Okay. Yes.
I've always wondered, and it's not shown in this picture, but if we stand outside and it's dark enough, which it isn't here, and we can see, the Milky Way above us, are we seeing what's still in our spiral?
Okay, so you're asking,
are we looking through to some?
All right, how far out into the Milky Way can we see? With the human eye, you're seeing just a small region of the Milky Way. There's certain things that you can see that are really far away, but all of the stars you can see with the human eye are about the size of a sausage on a 16-inch pizza. Okay, that's the volume that you can see. And maybe if you include all the other stuff you can see, it gets out to the size of a pepperoni on a pizza. But you really can't see much further than that. Okay. Questions about the news story, because I don't want to eat into Will's time. Yeah.
In the arms, is that dust or are there stars in there?
Yes, within the spiral galaxy, we have a lot of dust and we have a lot of stars. The spiral arms contain both.
These arms that are.
Oh, these Magellanic streams. No, this is just I assume it's hydrogen gas that you would detect in the radio. There will be some stars in this, but it's not a place where stars would be made because it's very diffuse material. Okay. Second story. Exoplanet helium. All right. So we all took chemistry. How many of you took chemistry, or will take chemistry for the young kids in the audience? Right? Put your hands up. You're going to take chemistry, right? Peter, you're going to make sure she takes chemistry. Okay, good. All right. If you took chemistry, you remember the periodic table of the elements, and maybe you remember it with dread, but it's a really cool diagram, okay? It really puts things in lots of order. But there's a ton of elements out there, okay? There's a lot of really interesting stuff out there. But for the universe, we can simplify it. We really only have to look at up here and up here, because when we look at the content of the universe, it's 75% hydrogen, 23% helium, and 2% other, and that's by mass, okay? So it's mostly hydrogen, helium, and then, there's all that other stuff, okay? Which is why we astronomers talk about hydrogen, helium, and then heavy elements, okay? So when we look at that, we can see hydrogen, helium. If we look at our sun, the composition of our sun, well, that's pretty much the same. Hydrogen, helium, and all this other stuff, okay? All the stuff that you really think of, that's just, that's in the noise. And even when you look at the giant planets, Jupiter, Saturn, Uranus, and Neptune, this is a table you can see. Now, this is not by mass, this is by number. 86 and 13, 88, 82, 80, 19, 15. Most of all the stuff is hydrogen and helium. All right. So that's setting you up to understand that this is really expected to be everywhere in the universe. So we have found 3,000 extrasolar planets out there. And a lot of these extrasolar planets, we detect them via the transit method, where the planet passes in front of its star. And for certain ones that are nearby, when that planet passes in front of its star and it's close enough to that star, some of the light of the star goes through the atmosphere of that planet. And if we take a picture when it's in front and when it's not in front, and we subtract the two, we get the spectrum of the atmosphere of the planet. We can examine the atmospheres of other planets. And so, for example, here is an example spectrum of a planet called WASP 39b. And these features here are associated with water molecules, and these are associated with carbon dioxide, and this is potassium, and this is sodium, and we have seen methane, and we see ammonia. We have seen all sorts of species out there. but we've never seen helium, which, if given the intro that I did for this, is kind of strange because you would expect, hey, there's a lot of helium out there, and we have never seen it until, obviously, WASP 107b. Okay, this is an artist illustration of it. Well, it's actually, this is not WASP 107. This is the sun acting as a stunt double for WASP 107, and this would be WASP 107b drawn in this. And you can see it's got this very extended. In WASP 107b, using infrared spectra, we were finally able to detect helium in the atmosphere of a planet. And you might say, well, why did it take this special? Well, first of all, previous observations had been using visible light and ultraviolet light, and they did not find the helium. And it turns out that the interesting lines that you want can be found in the infrared, but also WASP 107b is one of the lowest density giant planets we've ever discovered. Okay, it is the same size as Jupiter, but it's only 12% the mass of Jupiter. That's really low density, and these giant planets aren't very high density to begin with. Okay. They say that Saturn would float in a bathtub, which is kind of funky, but anyways, it's lower density than water. All right, this is really, really low density, which means its atmosphere must be really, really extended. It must extend tens of thousands of kilometers out into space. And it's because it's such a low density planet, it has this really extended atmosphere. It's in close to its star. And they did the observations in infrared that they've finally been able to discover helium in other planet atmospheres. We always knew it and expected it would be there, but it's really kind of nice to find what you expect and not be missing one of the two primary elements in the universe in extrasolar planet atmospheres. All right. And so that's our news summary for tonight. Any other questions on the two stories I presented to you? Yes.
Doesn't that beg the question of why didn't we find it in all the other planets?
So the question of why we didn't find it in all the other planets is because this is an extended atmosphere. Without the extended atmosphere, the helium layers weren't exposed. Okay, that's the current understanding. We'll have to detect it in a few more planets and a whole to get a statistical sense of when we can see helium and when we can't. But now we know how to find it. We will look at the other ones and see if we can get enough to make a statistical argument as to exactly why we're not seeing it in any of the others. Okay? All right, thank you. All right, so our featured speaker tonight is Dr. Will Fischer from here at the Space Telescope Science Institute. He got his undergraduate degree at the University of Toledo, then went on to do a postdoc. Was it Goddard first or? Toledo for the postdoc. Toledo for a postdoc, and then to Goddard for that. And then he came. Did you come here from Goddard? Yes. Okay. So he came to us from Goddard only a year and a half ago, and his work is as a support scientist for the Cosmic Origins Spectrograph. And when he is not doing his astronomy, he is a father of an 11-year-old girl who has got an interest in astronomy, he tells me, but from a special perspective, she likes to explore the art of astronomy and art. So he's leading his daughter into not just a STEM career, but a STEAM career, science, technology, arts, and mathematics. So ladies and gentlemen, Dr. Will Fischer.
Well, thanks for coming, everyone. To start here, I'm showing you a picture of Orion from Bayer's famous atlas of 1603, and he's looking at an image of Orion from the infrared astronomy satellite, which orbited in the 1980s, and you might imagine that Orion is a little bit puzzled to learn what he's really made up of. I'm going to be telling you all about star formation in Orion and how we learn about this with a lot of different space telescopes and a few that aren't quite in space. So one of the reasons that we're interested in how stars form is all of these thousands of exoplanets that have been discovered over the last 20 to 25 years. This is an artist's rendition of some of those exoplanets, and they exist in a wide variety of densities and compositions. They orbit at some pretty surprising distances from their stars. And to understand how all this comes to exist, we have to know how the parent stars form. So this has given new importance to studies of star formation in the past few decades. But star formation began quite some time ago. I think of 1852 as the beginning of star formation studies. This is when this astronomer pictured here, John Russell Hind, discovered a nebula that we now know as Hind's Nebula, and there was a star in that nebula called T Tauri. If you see a star where its name begins with one or two capital letters, that means it's a variable star. T Tauri, as a variable star, changed in brightness somewhat irregularly over periods of days to weeks. But the interesting thing about this discovery is that the nebula also varied in brightness along with the star. So that's a sign that the star and the nebula are physically connected. The star is embedded in the nebula. People didn't know what to make of this at first, but as time went on, more of these T Tauri-like stars were discovered, and then finally, in an important paper in 1945, the astronomer Alfred Joy laid out the class of T Tauri stars. Often a class of objects in the sky is named after the first one to be discovered, and this is an important step in putting a science together, to go from a single object to understanding that there's a collection of objects that all have similar observational properties. This is a light curve of an example of a T Tauri star, and when you plot a light curve, high points are bright and low points are dim, and you plot those against time. So you can see over the course of about a month, you have these irregular variations in a T Tauri star. And the change in brightness here corresponds to about a factor of 10 or a little bit less than 10. And he recognized that there were 11 known stars that had light curves like this, and they were all in nebulous regions of the sky, in these clouds. So these must all have something to do with each other. And people started to try to make some sense of this. Scientific understanding began to develop. And this is Cecilia Payne-Gaposchkin. She is my daughter's scientific hero, I guess you could say. She is the one who discovered what stars are made of, that they're mostly hydrogen and helium. Nobody believed her for a few years because this was such a radical idea, but eventually people came to realize that she was right. After some of her most important discoveries, she began to write about science and astronomy for public audiences. Here in 1952, she said, perhaps the nebula is in some way responsible for their very existence. So people were beginning to figure out that maybe stars formed from nebulae. And this is one of the earliest photographs of the Orion Nebula. So you can see there are several stars that are potentially embedded in that nebula. It all came together when two astronomers were able to make sense of it all. So on the left here is Victor Ambartsumian. He was an Armenian astronomer, which meant that at the time he was working in the Soviet Union. So people outside of the Soviet Union had a pretty limited understanding of the science that was going on there. And then independently, George Herberg, who was on the faculty at the University of Hawaii, both argued that T Tauri stars must be young. They are clustered. Here's a cluster of many, many T Tauri stars. It's a Hubble image of NGC 3603. And not only are they clustered, but they're embedded in these clouds of gas and dust. So these are signs that these are young stars, that they have formed from the nebula itself. And this was philosophically an important advance in the thinking of astronomers. For millennia, people had imagined that the universe had all come together and was formed sometime in the distant past. Then humanity showed up, and it was our job to figure out what was already there. But this was one of the first signs that the cosmos was still in the act of forming itself, that new objects and new potential places were continuing to form out of the original materials of the universe. So we are in an evolving universe. Today we know of thousands of young stars in various star-forming regions. Here's the Orion Nebula, And then these are some other star-forming regions in our galaxy, where you can see these young stars forming from gas and dust clouds. Now, this is our conceptual picture of how these stars form. You have these huge clouds of gas and dust that can give birth to thousands of solar systems. And in small regions of those clouds, you might have just enough material that the gravity of that material is powerful enough to cause it to start collapsing. So early on, you have a dusty envelope that's collapsing and becoming more and more dense and hotter at its center. After about 150,000 years, most of that envelope has formed into a central star. But the material doesn't just fall directly onto the star. These cores are spinning very slowly, and anything that spins as it falls inward, instead of forming just a central sphere, it's going to first form a disk. So this disk forms, and it progresses to feed onto the star. So for a few 100,000 years, you have a star with a disk, kind of a remnant envelope still falling onto the disk, and then some fraction of that material gets ejected from the poles of the stars, carving out a cavity in the envelope. And sometimes you can see some pretty dramatic outflows, gas being launched from the star. After about 500,000 years, the envelope is gone and you're left with a disk orbiting the star, and that disk may be forming planets. That's a really hot topic of research right now. How early in the formation of a star do you see planets? And the signs are starting to point to planets forming almost as soon as the star does. There's a lot of debate if you see gaps in a disk. Does that necessarily mean there's a planet there? Or could some other process be giving the signposts of planets? After about 2 million years, plus or minus a million years, it varies a lot from system to system, that disk is gone and you're left with planets orbiting the star. And this is a very stable situation. In many cases, it lasts for billions of years. Now, where are stars forming in our galaxy? This is an artist's rendition of the Milky Way by Robert Hurt at the Spitzer Science Center. And you can see the sort of dense central bulge of our galaxy and the spiral arms. The stars are forming in the coldest parts of the galaxy. You can see these little brown clouds here. These are cold molecular clouds. They're so cold that the gas remains in a molecular state instead of in atomic form. So they're cold and dense, and they start collapsing, like I was showing you on the previous slide, to form these new stars. To really study where the stars are, though, we have to use more than just the light that meets our eyes. So star formation is really a challenge for multi-wavelength astronomy, where we're using not just visible light, but ultraviolet light, infrared light, radio waves, all these different wavelengths of light that can reach us. The best way to map the large-scale distribution of gas that forms stars is by doing radio astronomy. This is the 5 College Radio Astronomy Observatory. It no longer exists, but it was on a peninsula in western Massachusetts that extends into the Quabbin Reservoir. It reached the end of its scientific lifetime, and this is kind of a natural preserve. So the agreement was they had to disassemble the radio telescope after they were done doing science with it. But this is an image it made of carbon monoxide gas in the Taurus star-forming region. Carbon monoxide is far from the most common component of these molecular clouds. It's mostly hydrogen, molecular hydrogen. But carbon monoxide is really easy to detect. So if you're going to map a star-forming region, that's a good way to go. And you can see in this image this filamentary structure, these long sort of trails of gas that's bright to a radio telescope. And these trails are where they're called filaments, and these are the dense regions that are likely to form stars, and in fact are forming stars in Taurus. I'm going to be telling you mostly about what you can do with infrared astronomy in our multi-wavelength study of star formation. This is Barnard Dark Cloud 68, and you can tell why it's called a dark cloud. It's a cloud, and it's dark. And you can see how this is a very dense star field, but around the cloud, you see some reddened stars around its edges, and then in the center, almost nothing pops out. And this is a visible light image. If we look in the infrared, it's a very different situation. This is an infrared image, and suddenly we see hundreds of stars poking through the cloud. The advantage to infrared light is that it lets us see through the dust. The infrared light escapes more easily through this dust, and it's also sensitive to objects that aren't hot. Astronomers tend to play fast and loose with their temperature words. We'll talk about cool things that are actually hundreds of degrees. But this infrared light is really sensitive to things that aren't as hot as stars yet. They eventually will be, but they're from a few hundred to a few thousand degrees. That's where the infrared is really most useful. Here's Orion in visible light, the famous constellation, the 3 stars in the belt. Betelgeuse is a red supergiant in the shoulder of Orion. Rigel is a blue supergiant down here at his knee, and you have his sword hanging from the belt. The Orion Nebula is this faint fuzzy patch here. And so visible light detects stars. But here's Orion in the infrared, the picture I showed you at the beginning. You don't really see many stars in this one. Betelgeuse, because it's such a bright red star, still pops out in the infrared image, but Rigel and the belt stars are totally absent. And you see these bright regions where the stars are forming. The Orion Nebula is now the brightest thing in the image. And you can see that in Orion you have these bright star-forming regions extending kind of all up and down the southern half of the constellation. So the infrared is really the key to telling us where the stars are forming. And why is Orion so important from a star-forming perspective? We have thousands of young stars in the Orion Nebula alone, but it's really just the centerpiece of this huge star-forming complex. If you were to draw a circle around our solar system that was about 1,500 light years in radius, encompassing many of the nearby stars that are all familiar to us, Orion contains more than half of the young forming stars in that region. It's the nearest place where the most massive stars are forming. So you really see the full spectrum of stellar masses forming in Orion. And we can also probe a lot of different star-forming environments in Orion. On the left is one of these Barnard dark clouds. This is not in Orion, but it's just an example of isolated star forming. You have this really dense field of advanced, more aged, older stars, and then this dark cloud that contains maybe one or a few forming stars. Here is part of Orion. OMC 2-3 is the Orion molecular cloud 2/3. It's just a part of the Orion molecular clouds. And this is an example of clustered star formation. You can see these dark, dusty filaments with young stars all along them. So in Orion, we can really get a sense for how stars interact with one another as they form. There are even different environments within Orion. This is a map of cold dust in Orion going from the Orion Nebula far to the south. And then these are insets where we zoom in on a couple of these regions and look at how stars are distributed in them. This is a very densely populated star-forming region within Orion that you might think of as a city. All these circles mark the locations of young stars, what we call protostars. And the size of the circle tells you how luminous it is, how bright it is, how much light it's giving off. So in this part of Orion, you have very dense clusters of stars that are quite luminous and all interacting with one another. Farther to the south, we have what you might think of as the suburbs, where there are fewer stars. There's less background emission from local gas and dust. The stars are less luminous, and there's a little bit less going on there. So it really is sort of an experimental lab to see how stars form in different environments. So I'm going to tell you about how we've used different space telescopes to understand star formation in Orion. And it begins with the Spitzer Space Telescope. This is a 0.85 meter telescope, not huge compared to a few of the ones we'll be discussing. It launched in 2003, and these infrared space telescopes, they have to be cooled to be most effective. They're about the same temperature as the objects they're trying to detect. So if you don't cool them, they're going to detect themselves, to put it simply. So you have to cool them down, and you do that by putting some kind of substance aboard, some kind of cryogen to keep it cold. Cryogen loses its effectiveness after a while. So Spitzer launched in 2003, but it ran out of cryogen in 2009. It's still effective at some level. It has limited capabilities, and it's continuing to send back data. And it's in an Earth trailing orbit. This is approximately where it was when I put the slide together. It's about the same distance from the sun as Earth, but just a little farther out. So it orbits a little bit more slowly, and it loses ground on Earth as each year goes by. So that's another thing that's limiting its capabilities. As it's farther from Earth, it becomes more difficult to communicate with it. But it's been a very productive space telescope so far, and we used it to survey Orion. This is a Spitzer map of part of the Orion molecular clouds. You can see all of this bright gaseous material, dark, dusty lanes, and young stars that are forming. This schematic gives you a sense for why an infrared telescope is good at detecting young stars. A plain old star, its light output peaks at wavelengths that we can detect with our eyes, at visible or optical wavelengths. And then its light distribution falls off pretty rapidly as you go into the infrared, the longer wavelengths. But if you have a disk of relatively cool dust around the star, that's bright in the infrared. So instead of your basic star, the spectrum of the star, its energy distribution, falls off a lot more slowly through the infrared, and thus infrared space telescopes are really good at picking these out. So we can see the real-life equivalents of these cartoons I showed you earlier, where you have the very young protostars, where there's an envelope falling onto a disk, and then the slightly more advanced young stars, where most of the envelope has been cleared away. Once we identified all these young stars with Spitzer, we continued with Herschel. Herschel was primarily funded by the European Space Agency, but it also had contributions from NASA. It's a big one, 3.5 meters in diameter, its primary mirror, and it operated in the far infrared. So Spitzer was sort of mid-infrared, Herschel is even longer wavelengths. It launched in 2009, ran out of cryogen in 2013, and all of Herschel's instruments required cryogen to operate, so it's no longer producing images for us. It is at a special point in space called L2, the second Lagrangian point. At L2, the Earth's gravity and the sun's gravity balance out, so you get a stable orbit, even though you're kind of far away from Earth. In fact, the L2 point is 4 times farther away than the moon. It's really out there. So unlike a telescope in low Earth orbit, you can't go out to L2 and fix things, at least not yet. So after Herschel's life cycle was over, that was the end of its science. But L2 is a great place to put a far infrared telescope. It's a stable orbit, and things are also cold there. So you really get a great view of the infrared sky from L2. And it's not the only telescope that's currently there, and additional ones are going to join it. I'll mention that later on. The advantage to Herschel is that we could follow up on these protostars that Spitzer had identified. We conducted HOPS, that's the Herschel Orion Protostar Survey. These are some members of the HOPS team at one of our meetings in Granada, Spain a few years ago. With Spitzer, we found more than 500 of these protostars. These are young stars with the dusty envelopes that are just beginning to form. And then we followed up on more than 300 of them with Herschel. So this map, the dark shading tells you where the dust is in Orion. All up and down the Orion molecular clouds. The Orion Nebula is here. And then these circles mark the locations of protostars that we followed up with Herschel. All these little thumbnails here are actually Spitzer images that give you a sense for the environment, whether it's crowded with bright backgrounds or maybe somewhat less crowded with a dim background going from the city out to the suburbs. So we did all this follow-up with Herschel, and this really gives you a sense comparing Spitzer data on the left to the combination of Spitzer and Herschel on the right. This shows you what you can do with the far infrared. Spitzer, the dustiest regions in the cloud are dark. They're cold. They're not really emitting very much at the mid-infrared wavelengths that Spitzer detects. So you have these dark dust lanes, and then you can tell where the stars are, but the really deeply embedded young ones, you can't learn very much about them because they're faint. Here, the blue is from Spitzer, but then the red and yellow we're bringing in the Herschel data. So there are two things to notice here. First of all, some of these faint protostars in the Spitzer image are now some of the brightest ones in Herschel. There are two here, there's one up here. These really bright Herschel protostars, those are the really young ones. Those are the ones we can study to learn exactly what's going on as gas and dust begins to condense from the molecular cloud to form stars. The other thing to notice here is that the dark dust lanes are now glowing. At the longest far infrared wavelengths, you can really see where the dust is and see how intense and how much dust there is by how brightly it's glowing. So this really allows us to understand everything that's going on in a star-forming region when we combine the mid-infrared and the far-infrared light from Herschel. I want to tell you about one of our first HOPS results. We're going to go back in time from the Herschel Space Telescope to Herschel the astronomers. William Herschel and Caroline Herschel, they're shown in this painting here. They were some of the best astronomers of their time, working in the 18th century. And William Herschel was conducting a survey with his telescope of the Milky Way, and he discovered dark patches. And he said, he spoke German, but what he said was, truly there is a hole in the sky here when he saw these dark patches. This is one of the dark patches that he talked about. This is what we today call NGC 1999. This is our first Herschel image. We bring in some Kit peak data, that's in blue for context, that's optical, possibly near-infrared imaging. We see some of our Herschel protostars here. And then this is a Hubble close-up of this NGC 1999 region. It's one of these holes in the sky that William Herschel noticed. It turned out that Herschel's holes in the sky are mostly these dark dust clouds, like we were talking about before. This is NGC 1999. This is Barnard 68 that I showed you before, where the dark cloud is, it's not a hole, it's a dark dusty cloud. And when you look in the infrared, you see lots of stars here. But in this particular case, NGC 1999, it's a little bit different. This is the Hubble image I showed you, but then when you look at Herschel images in the far infrared, the hole in the sky is still a hole. If there were dust here, it would start to glow in the far infrared. When we go even further out into the infrared, it's still dark. So there's no dust there, it would glow. And here in this very deep near-infrared image, we see a star through this hole in the nebula that's not particularly red. So we're actually seeing through empty space here. This one really is a hole in the sky. So it was kind of a neat discovery we made. Herschel, the astronomer, said something in 1774, truly there is a hole in the sky here. 236 years later, the telescope named after him confirmed that he was right about this one. And this was the beginning of our HOPS project. Another really key discovery with HOPS is that there were protostars in Orion that Spitzer missed. They were too faint in the Spitzer images for people to realize that they were protostars. So these are some thumbnails of two of these protostars. The top row are Spitzer images. This is kind of the near to mid infrared wavelengths that are a little bit longer than our eyes can detect. And here in these two circles, you see a faint object here and a brighter object here. If you go out to some of the longest wavelengths that Spitzer was able to effectively work at in Orion, you see nothing in this top circle and just a very faint blob in this bottom circle. We weren't sure what these were just based on this information alone. They were classified as galaxies to the extent they were classified at all. But when we looked at them with Herschel, they really jumped out. All of a sudden, they're the brightest point sources in this field. Down here at the bottom, we've gone out to sub-millimeter wavelengths. This is almost in the radio at this point, where we're detecting very cold dust, and they remain bright there. So this is a sign that Herschel was able to detect protostars that Spitzer missed, and because you have to look at such long wavelengths to see them, that means they're among the coldest protostars in Orion, and therefore the youngest. Our estimates are that they may have formed only 25,000 years ago. Now I say only, that seems like a long time. But if you remember back, I told you it takes on average 2 million years for a star to form. 25,000 years is a tiny fraction of that. So Herschel really allowed us to complete the census of protostars in Orion and really see what was going on in the very youngest systems. This is a larger scale image of these new protostars. Spitzer is on the right, and again in these 4 circles, these are the 2 I showed you before. There are a couple more down here to the south. There's almost nothing in Spitzer. But when you bring in the Herschel far infrared data and the apex submillimeter data, they're very bright. So we can really understand all of the secrets that Orion has to offer by going to the longest wavelengths. Now that the Herschel project we've had all of our Herschel data for a few years, and most of the science has come out. There are still a few papers lingering along that we're trying to get into the literature. But we've turned to detailed follow-up of some of these protostars with Hubble, for instance. With Hubble, once we know the protostars are there, we can zoom in on them and get very high-resolution images compared to what we can get with Spitzer or with Herschel. Now, Hubble has a lot of different instruments. I work on the cosmic origin spectrograph, which is optimized for the ultraviolet, but for science, we tend to use, for the science of star formation, at least the sort of work that we do, we tend to use the near-infrared cameras on Hubble. There's NICMOS, which was an earlier generation instrument, and then WIFC-3 is Wide Field Camera 3, which, as you can see, gives us a wide field of view, and we can see high-resolution images of many protostars at once. So here we can see some edge-on protostars where we're looking through a dusty disk, and we can see some of the outflow cavities. Here we see some point-light protostars where maybe we're looking more pole-on and just seeing the light from the central regions of the system. And we can see all sorts of details about exactly how gas and dust are distributed around these stars. And this is just a demonstration of what you can really do with the high resolution of Hubble. In the 1980s, if you looked in review papers, you would see these cartoons showing how stars and disks and maybe outflow cavities worked. Well, when we did our Hubble imaging, we found, it was almost as though the cartoons had become reality. Here in this image of a star called HOPS 136, we can see everything that people predicted in these cartoons 20, 30 years ago. We see these dark lanes, which is the sort of circumstellar disk seen in projection. We see these bright nebulae from the upper layers of the disk. The disk casts a shadow here. We can see light being scattered off the inner edges of the envelope and then the outflow cavities. So it's all there, just as the theorists of the 1980s were predicting. One of the things we can do with these Hubble images is study multiple systems. So protostars rarely form as single stars. They tend to form in double systems or triple systems. Sometimes you even have quadruple systems. Something about the way stars form leads them to form in pairs or even greater systems. And here are some examples of these. Here's a binary system where the top one is one of these edge-on disks where you can see this dark lane and then some nebulosity on either side of it. And then the southern member of the pair is seen more pole-on, so the light from the central regions is escaping and it's just a point of light. Here's a triple system, a double system where this more distant one might be related, and here's a very close double. What's interesting about these young stars, they form in these little clusters of 2 or 3 or more stars, but then if you go look at main sequence stars, more evolved ones, you don't see nearly as many pairs. You still see a lot of them, but not quite as many. So something about the way these stars are interacting through their gravity, the third member of a system might get flung out. So you're left with just a binary system where there used to be 3. It's possible that the sun may even have formed in one of these small collections of stars that was disrupted by gravity. Another exciting thing we can do with these Hubble images is to study the cavities and the outflows. Here you can see all sorts of different morphologies. It's pretty surprising. They're not at all alike. You have examples up here of bipolar systems where you have this dark lane and then the 2 nebulae on either side that are pretty symmetrical. Here you see this huge system that's a little bit asymmetrical. Here's kind of a smaller, more tightly contained one. This one side of the nebula is much brighter than the other. Down here you have all sorts of structure, like there have been maybe multiple outbursts from this system in the past. This bizarre ring-like structure. Here's a very wide-angle outflow. There's lots going on here. And we think that one of the important things these cavities do is these cause star formation to slow down and eventually stop in a star forming region. The outflows being launched from the star disrupt the cloud, and eventually there's not enough dense material to continue forming stars. So we think this is a clue to how star formation ends. ALMA is another facility, this one on the ground. ALMA is the Atacama Large Millimeter Array, where millimeter refers to the wavelengths of the light that we're studying. And as an array, it's actually a collection of sort of medium-sized radio telescopes. They're not quite radio telescopes, but they work like them. And by using an array of telescopes, you can get some of the benefits of having a single large telescope, but you can kind of reconfigure the different dishes to study physical structures at different scales. ALMA is on the ground, but it's kind of almost in the sky because it's 16,000 feet above sea level, one of the highest flat places on the Earth's surface. Up there, the air is exceedingly dry. It really doesn't rain there ever, and exceedingly thin. So it's almost as though you're in space. These are images of protoplanetary disks in Orion. So we're looking through the envelope and imaging the disks themselves. And the important thing here is, for comparison, if something just like Neptune were orbiting one of these stars at the same distance from its star as Neptune is, you would be able to, resolve the orbit of Neptune. So we're really getting to the point where we can witness not just stars, but the solar systems, the systems of protoplanets themselves in the act of formation. This is really cutting edge science, and ALMA is continuing to get more powerful and more able to resolve these fine structures. So there are lots of debates going on right now about which stars have planets and which ones are maybe just beginning to form planets. I want to talk a little bit about the science that I'm doing in particular with star formation in Orion. So I'm interested in outbursting protostars, and I'll show you what I mean by that. This is a wide field image of Orion, starting the Orion Nebula is off the top of the page, and then this is this kind of suburban region of Orion that I was telling you about. The circle toward the bottom of the image marks the location of HOPS 223. It's fairly isolated. It's part of this little group of 3 young stars. This is a near-infrared image of HOPS 223 and friends in the late 90s. HOPS 223 is pretty faint compared to the other 2 objects in the field. But when we came and looked again in 2011, it was suddenly much brighter. Now the brightest object in the field. So something happened here that may tell us about how stars form. This is a Hubble image of HOPS 223 and friends. This is HOPS 223. This is HOPS 221 down here. The numbers are not quite randomly assigned. They don't mean a whole lot. But this is just a little collection of stars, and HOPS 223 is undergoing one of these outbursts. We think that the reason these get so much brighter is because they suddenly begin this episode of rapid mass accretion. They're maybe gradually accreting material from their circumstellar disks over a period of thousands of years, and then suddenly something happens to cause material to pour onto the star much more rapidly. These are light curves. If you remember way back near the beginning of the talk, I showed you a light curve of a typical young star. These are light curves of 3 famous outbursts. This one here was a pretty normal star in about 1935, but then suddenly, just in a span of months, it became more than 100 times brighter, shot way up here. And ever since then, for decades, it's been slowly trailing off in brightness, but it's still much brighter than it ever was beforehand. And there are a couple of other objects that were detected back in the 20th century to do this, and we've started finding more and more of them more recently. So these outbursts may actually be essential for the formation of a star. We think it's possible that most of a star's mass might be assembled in a series of a few dozen of these outbursts over the 2 million year star formation period, rather than as a slow and gradual process. A lot of theorists have put together simulations of how these outbursts work. So a little bit about the physics of star formation. This is a scenario, so in this image, the star is here at the center in yellow of the system. This is all disk material. So the star's disk is gradually drifting inward, trying to accrete onto the star. But the star's got a magnetic field. It's just like a bar magnet. It's got a north pole and a south pole and a magnetic field. That magnetic field keeps the disk from coming in all the way. So then the material instead flows along these field lines and crashes into the star at high latitudes. We call this magnetospheric accretion. It's the accretion of gas through the star's magnetosphere. But when an outburst begins, there's maybe some blob in the disk that's much denser than the rest of the disk, and when that accretes, it brings a lot more pressure with it. So the disk plows into the surface of the star right at its equator. It completely overwhelms the star's magnetic field, and some of that material gets shot off along the poles to form these outflows. So it's an entirely different scenario for these stars getting built up. And this seems to persist for maybe hundreds of years. All of these outbursting stars, we've never seen one of the major outbursts turn off completely. So it's unclear how long these persist. I used one more space telescope called WISE. This is the Wide Field Infrared Survey Explorer, and it's one of the smallest ones, probably the smallest one we've discussed so far. It's kind of a small but mighty space telescope, though. It was launched in 2009, and it did a survey of the entire sky. It was very flexible. It did an all-sky survey in 2010, and it's continuing to orbit the Earth, performing a search for near-Earth asteroids, which is pretty important if you think about it. This is an image of the Milky Way from the WISE telescope. And we actually used it to search for more outbursts. Spitzer made a map of Orion in 2004. WISE came around in 2010 and did the same thing. And we could do a computer-based comparison of the two maps to look for stars that got much brighter in the intervening time. We had one really great find of an outburst. When I was a postdoc at Toledo, Emily, shown here, was working with me on her senior thesis and discovered HOPS 383. An outbursting protostar in Orion. This is a fairly large image of part of Orion with the nebula here. HOPS 383 is just to the north of it, along one of these dark filaments that I've been talking about from time to time. These are the Spitzer images of HOPS 383, where you can barely see it at the shortest Spitzer wavelengths. Pokes out a little bit here, and then at the longest Spitzer wavelengths, it's faint. Nothing you would have imagined was a protostar, maybe some kind of background contamination or something. But here it is in WISE. Look how bright it is at the longest WISE wavelengths. This was an unambiguous sign that something happened in this object. Something made it get a factor of a few dozen brighter between 2004 and 2010. This is actually the youngest known outbursting protostar. It's barely visible at the shortest WISE wavelengths even now, and it's extremely bright as you go farther and farther out into the infrared. That means it's young and deeply embedded. It's maybe 100,000 years old, give or take. It's hard to date these things precisely, but it's young. So even in their earliest stages, these stars undergo these outbursts, which is evidence that this is a really important aspect of star formation. This was enough to generate a press release. Here's an image from our press release showing the before pictures here and the after pictures in the bottom row. These are near-infrared images from Kitt Peak. And what we found, so we have over 300 protostars here. 2 of them began outbursts in a period of a few years between 2004 and 2010. There's HOPS 223 that I started off talking about, and HOPS 383 shown here. That's kind of small number of statistics. But it's an indication that any given protostar may have an outburst like this once every 1,000 years. That's where that number comes from, that a protostar might do this 50 times over its formation period. So these protostars are active young stars engaging in some pretty dramatic fluctuations in their brightnesses. The last, or just about the last, observatory I'm going to tell you about is SOFIA. This is not technically a space-based observatory, but it comes pretty close. This is the Stratospheric Observatory for Infrared Astronomy. It's actually a passenger plane that has been turned into a telescope. You see this large rectangular opening in the back of the plane. This plane takes off every night from Palmdale, California, in the desert near Los Angeles. Sometimes it can observe the southern sky by taking off from New Zealand. And after it reaches cruising altitude, this door opens up in the back of the plane to let the telescope peer out into the mid-infrared sky. The cool thing about SOFIA is that astronomers who get time to use SOFIA are able to fly on it. So you can kind of see the whole flight operations crew in action. This is a view from inside of the observatory, where instead of tightly packed rows of economy seats, you see all of these scientific workstations, also tightly packed. There's a flight commander that sort of makes sure the pilots and the scientists understand what each other's trying to do and make sure everything goes smoothly. You have instrument scientists on board, and then the astronomers who got time are just kind of there trying not to cause too many problems and trying not to interfere with the process too much, but just learning how it all works. In the back of this image, we're actually seeing the right side of the telescope. The telescope's peering out of the plane this way. And this is, just the side of the telescope, and the instruments get attached there that detect and record the light. And SOFIA flies pretty high. Many of its observations are conducted from 37,000 feet, but to go out to the longest wavelengths, it goes up above 40,000 feet, where the air is, as thin as you can get access to, and as dry as you can get access to. So it leads to some fairly sensitive infrared studies. It's not quite as sensitive as a Spitzer or a Herschel, but it lands every morning, so you can go and fix things and improve things. Yeah, question?
Is the telescope kind of like isolated from the computers that hold up signatures?
The telescope is isolated in that sense, and it's kind of interesting to watch it when you're flying because it looks like the telescope is rotating, but it's actually the plane sort of moving around, and the telescope is engineered to remain steady. Yeah.
So how does it compensate for the vibration of the plane?
Right. I don't understand the details precisely, but it's isolated in such a way that it can move freely, or rather, stay put while the plane vibrates. So this is our image of HOPS 383 with SOFIA. It's this faint fuzzy blob in the center of this circle here. So with SOFIA, we're just barely able to detect something deeply as embedded as HOPS 383. But we can detect it well enough to know that it's still in outburst mode in 2016, 10 years after the outburst began. And this is currently the best way we have of monitoring outbursts in the infrared. Coming along a few years down the road, though, is James Webb. And from the perspective of somebody who studies star formation, Webb has two advantages. It's going to have the detailed high-resolution view of Hubble, but also the infrared capabilities of Spitzer. So by combining those two, we can really begin to look at the most deeply embedded protostars, study how often they have outbursts, and start to learn something about the precise physical conditions that exist in the innermost regions of those young stars. This is just some text from one of the JWST science themes to show that star formation is supposed to be one of the hot topics that Webb's going to address. So just to wrap things up here, this is a whole gallery of all the different telescopes, from the ground with ALMA to the stratosphere with SOFIA to space with all of these guys. And they're really beginning to reveal the secrets of star formation in Orion. And this is how we learn how our sun formed. All of these young stars in the Orion molecular clouds, their average mass is a little bit less than that of the sun, but we expect many of them to form planets and go through a cycle of sorts just like our sun does. So this is really our best way to figure out how the sun and planets all formed 5 billion years ago. Thank you. Yeah, question.
So you're looking at a lot of stars. Have you been able to see these go through?
Well, so you're referring to when nuclear fusion begins in the core and it becomes a true star. It's a little bit difficult to see that in the act of happening just because it's such a slow, long process for what's happening in the core to propagate outward. We see lots of stars that are kind of on both sides of that boundary, though. So. Let's go into the back.
With your research, do you have any feel as to how many stars actually develop planets? is what percentage would be?
Oh, okay.
So the question was, do we have an idea of how many stars create planets from this work?
From this work and from other work, it looks like nearly all of them do. I mean, everywhere we look, stars have planets. There's all sorts of evidence coming from these ALMA images of young stars that there's no such thing as a perfect disk. They're all distorted in some way that might be due to planets. It's kind of an open question still, but it looks like planets are a pretty standard outcome of the star formation process.
I mean, when you showed the disks from ALMA, I mean, ALMA's finding a tremendous number of these disks around protostars.
Right, right.
And it to me is the one that has the greatest resolution for seeing all these disks.
Mm-hmm. Yeah. Our disks in Orion, this is kind of a snapshot survey, but people who go look in fine detail at any given disk see a lot more structure than I showed you here even. Yes.
During the accretion process, what is the threshold minimum for matter to accrete, begin the fusion process, and so become a star?
So what is the minimum for minimum density, or
What is the threshold minimum for matter, the amount of matter necessary to
are you talking density, or are you talking
Well,
amount of material?
amount of material? You can,
All right. So what does it take for a clump of gas to collapse down and become a star? What are the thresholds it has to cross?
We often talk in terms of a mass accretion rate, and the units we use are solar masses per year. So a typical T-Tauri star might accrete at 10 to the minus 8 solar masses per year. That really means about 1 moon's worth of material is falling onto the star every year. That's not very much. Very early in the star formation phase, the accretion rates are maybe 10,000 times that. So 10 to the minus 4 solar
well,
masses
I was
per year.
thinking, what is that in terms of the minimum amount of matter necessary for the fusion process to begin?
All right. So the question, the minimum amount of matter necessary
How
for
much matter
fusion.
for the fusion is the
So
energy process
yeah,
of the star?
the brown dwarf.
The least massive stars that are fusing hydrogen in their centers are a little less than 1/10 of a solar mass.
Other questions?
Yeah, over here.
I have a question just about the Lagrangian points. Are they apt to get pretty crowded? I mean, it seems like several things being
All right,
sent.
so Herschel's already out of the L2. We're going to send Webb out to L2. Man, is it going to get crowded out there?
Yeah, the Planck Space Telescope is another one that's out there. They're not all like precisely at one point. They're all in various orbits around L2, so maybe crowded in a sense, but not that crowded. I don't think it's a concern that any of them would collide.
Geosynchronous orbit around Earth is much, 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 much more crowded. Okay.
Over here.
Do stars have an axis and magnetic poles, and if so, why?
Do stars have an axis and magnetic poles, and if so, why?
Well, yeah, they are magnetic. It's because the gas in these stars is so hot that the atoms dissociate into charged particles. So you have ions, protons and electrons, and the electric charge also generates a magnetic field. And in the less massive stars, you have these convection currents. So you get a current going with these charged particles, and that gives you a magnetic field. Yes.
Yeah, kind of the opposite of the first question. I know that things start to heat up when they collapse gravitationally. At what point are we able to start seeing it? I mean, how cold can it be?
All right, so it has to collapse and get dark. And when are we able to actually see the star? Is that what your question is?
Yeah, does something become visible?
Yeah.
With the Herschel telescope, we were detecting stars that had temperatures of maybe 40 to 50 degrees above absolute zero, 40 to 50 Kelvin. So we're getting cold, not quite as cold as like interstellar space, but cold. Yes.
But to begin to see them in visible light wavelengths, don't you have to have fusion?
Right. So to see them in visible light wavelengths, what has to happen? The fusion has to be turned on, of course.
So these T Tauri stars that I was talking about are what we call optically revealed. They show up in visible light images. They're not yet fusing, but the energy of contraction as the star gets smaller from its initial state to eventually become dense enough to fuse, that in itself releases plenty of energy. And once all that cloud is gone, it gets radiated as visible light. So even before hydrogen fuses, you can see optical light from these.
And a lot of that's geometric, of course, too, because if they're deeply embedded within the molecular cloud, you're not going to see them, whereas Orion is like a blister nebula, so we're able to see, there's a relatively clear line of sight, invisible at least.
Mm-hmm.
Well, another question about that Lagrangian orbit, like you often see drawings of that, and it looks like it's kind of perpendicular to the sun-Earth direction. What's the diameter of that?
So what's how big are these Lagrangian points, the area?
Like the
volume?
The orbit of the telescope would have.
Oh, yeah, I'm not sure what exactly the radius of the orbit around the L2 point is. It's large enough that the telescopes aren't colliding with one another, but I'm not sure. I'm not sure numerically what that is.
JWST, the Webb Space Telescope's librating orbit is really quite large. I mean, it's several Earth radii in diameter, at least. I don't know. I also don't know an actual number.
Because it's heavier than the others.
Yeah. Well, it's a nice big librating orbit around the L2 point.
Any idea about the length of life of a star-forming region?
So, what is how long does a star-forming region last?
Yeah.
That's a little hard to tell. We have some sense for how long the individual stars last, but you might get successive waves of star formation before the gas is fully exhausted. So you maybe will have if the average time it takes to form a star is 2 million years, maybe the star forming region itself could last for a few times that. Small, interestingly, compared to like geologic timescales. Like when the dinosaurs roamed the Earth, there was probably no Orion Nebula yet to speak of. Just for a little bit of a comparison there. Yes?
When you look at the Orion Nebula through a small telescope, you see these 4 stars in a trapezium arrangement. How do they relate to your talk tonight?
All right, so how do the trapezium stars at the core of Orion relate to what you're talking about today?
Well, those are the most massive stars in Orion, and those are part of what makes it such an interesting star-forming region. That's the closest star-forming region where you have stars that massive. And the winds, the outflows, energetic outflows from these stars tend to shape the entire dynamics and evolution of the immediate Orion Nebula region. They're largely responsible for a lot of the bright emission you see from the nebula. They may play a role in sort of blasting disks away from the lower mass stars. In my talk, I didn't touch on that too much because they were so bright to Spitzer that Spitzer actually couldn't image them. So we necessarily focused on kind of the more outlying areas of Orion, but they're really responsible for just a lot of what goes on in that central region.
I've been learning a lot about Orion as we did the visualizations of the Orion Nebula, and to see that giant river of gas in behind it and recognize that, all right, yes, this may be the city, but there's a tremendous number of suburbs within the OMC out there that there's the rich picture of star formation within Orion is so much more than we think of when we just think of the Orion Nebula.
One of your first references, the T Tauri stars, showed a plot where there was a significant variation in brightness over the span of weeks, maybe months, but within a year. I may have missed it, but what was the mechanism for brightness changes that quickly?
All right, so what's the mechanism for the quick brightness changes within the T Tauri stars plot you showed?
So if you remember the sort of schematic I showed of how material falls onto the star exactly, that's all happening over about 1/10 of the Earth-Sun distance, so a fairly small region, and just changes in the density of the accreting material due to pre-existing irregularities in the disk structure can cause those brightness variations. The accretion rate sort of goes up and down, and that leads to changes in the brightness.
All right, other questions?
Do we have any idea what was the cause of the holes that we actually have?
Yeah, so what caused those holes? If Herschel really is finding a hole, how did it get there?
That is probably due to those outflows that I've been talking about. All of these stars, they accrete matter, but then some fraction of that is pushed off along the poles of the star with some force. And that could actually blow holes in the nebula if you have a few of them that with the chance alignment, so they're all sort of collaborating on opening up a hole in the nebula.
All right, we got like two more, one here and one there.
What
Oh,
counts-
and one back there. That's three more. All right, go ahead.
What accounts for those strands of gas, those rivers you were speaking of, where you see all that star formation? Why are we seeing this sort of filament?
All right, so why do we see this filament or river of gas through Orion?
It seems like it's probably magnetic fields that are responsible for the filaments. You got these large-scale magnetic fields kind of threading the galaxy due to the motion of hot gas. And any gas that's even a little bit ionized tends to follow along those field lines. So that leads to these kind of stretched out filamentary structures.
Okay, we had one way in the back.
Yes, so we have detected gravity waves from two binary black holes and neutron stars collapsing together. But when a cloud of gas separates that into a binary star, does that form gravity waves?
All right, so gravity waves have been detected from two black holes merging together. The creation of these binary stars, would that also create binary gravitational waves? Does that summarize the question right?
These are much lower energy events than the collision of binary black holes. So there really wouldn't be any appreciable gravity waves from this. It's more just the clouds kind of relatively quietly collapsing into two stars on their own.
Okay, who had the last question there?
Your comment about the four trapezium stars together affecting the star formation area there, it implies to me that you're saying that all four of these stars are kind of physically clustered together, on an astronomical scale, of course. They're not 5 miles apart or anything, but they're clustered together. But I was always, from childhood, under the impression that when you look at a constellation up there, what you're really seeing is a flat field. And one star may be here, and the other one may be way the hell and gone over there. They just look like they're aligned in a pattern. Seeing them at their angular separation visibly. Is that not true then, or are other constellations those same stars kind of grouped together?
Okay, so
in depth?
the question is, all right, when we look at constellations in the night sky, the stars of the full Orion constellation, like Betelgeuse and Rigel, they're at totally different distances. But so how does that translate to some of this stuff we're looking at here?
Yeah, so in general, if you pick some random constellation out of the sky, the stars of that constellation have no physical relationship to one another. Orion's kind of an exception. Because everything I've been talking about here, this is a single, well, two really, clouds of molecular gas that are forming stars that are in close proximity. So all of the young stars in Orion are physically associated. It's kind of an exception to the usual rule about constellations.
Well, also, on the angular separation on the sky of the stars of the Orion constellation are much, 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 much larger. These are all very close. They're all basically in Orion, hanging down from Orion's belt in this area down.
You're talking about the Magellanic Clouds.
What?
Talking about the Magellanic Clouds.
You're talking about the Magellanic Clouds?
So maybe that's what you're talking about.
No, I'm not talking about the Magellanic Clouds. The Orion, the star formation in Orion is all in the area around the Orion Nebula, down below the belt. You're hitting Orion below the belt here. All right, Herman, do you have one last thing?
Yeah, interesting. I think I remember it right, but of the three famous stars in Orion's belt,
Alnitak, Alnilam, and Mintaka?
2,000 light years away, and the end stars are like 500 or 800 light years.
I actually, so he's talking about the stars in the belt being at totally different distances.
Yes.
I did a visualization of the main stars of Orion in 3D and spin it around. If you look on YouTube, you can find it, the Orion constellation in 3D, and it's one of our more popular ones for educational purposes because it takes Orion, you see it as it does, and then you spin it sideways, and it looks more like a stealth bomber than it does look like a hunter. All right, let's see. Next month is it's June, so July. I forget what our time. Oh, the Milky Way bulge, the blob from blob to remarkably detailed picture. That will be our July talk. Hope to see you all there, and let's give Will another big hand.
Thank you. Yeah. Thank you for organizing.
We have a lot of fun with this.